So far we got an introduction to rheological properties of the solids. We studied two properties, Young's modulus and Poisson's ratio, and we solved a couple of problems. Now let's learn a little bit more about it. In an ideal solid, the Hooke's law states that the stress is proportional to strain, and the proportionality constant is Young's modulus. So, suppose the material behaves like this, then this is non-Hookean solid, this is non-Hookean, this is the Hookean solid. So most biological materials follow non-Hookean behavior. Another thing is, in a Hooke's law states that when you release the force, it comes back to the original shape. There is no permanent deformation. But in a biological material, when you apply the stress, there is some recovered strain, which is the elastic strain. There is some permanent damage, like a dent, that is known as the plastic strain. So far we studied the ideal solid situation. Right now let's try to see the realistic situation. So a lot of time, this is the loading curve, okay? As the stress increases, the strain increases. It is not a linear curve. And when you reduce the stress, it comes back, and it may not come back to zero. So if you look at it, the slope is keep on changing, right? So there is not a single Young's modulus value. Rather, we use a term called apparent modulus of elasticity. We pick a point, typically the maximum point, and draw a linear line and find a slope. And just because it's not a Hookean solid, we use the term called apparent modulus of elasticity, which is equal to sigma max by psi max. Sometimes the sigma is a value selected at the inflection point, which we will learn a little bit later. Or sometimes it's at the rupture point, which we will learn later too. So it doesn't have to be maximum all the time. The one thing you want to know it is the apparent modulus of elasticity means it's the instantaneous modulus of elasticity at a given strain. So this is the elastic limit. So the Hooke's law is valid within the elastic limit. So that means within the elastic limit, if you stress it and remove the stress, they come back to the original one. If you go beyond the elastic limit, it acts like a plastic. There are some permanent damage occurs. So here is one of the real curves. So I have a stress versus the strain. Again, just to remind you, stress is force per unit area. The strain is deformation over the original one. This is the loading. This is the unload, right? So when it comes back, it reaches somewhere here. And this is the one rebound strain. Therefore, this is the elastic strain. And this is the one the permanent deformation happened. It didn't rebound back. Therefore, this is a plastic strain. So the percent elasticity is elastic strain by total strain times 100. Percent plasticity is plastic strain by total strain. So these are also properties of a biological material, because it is a characteristic of a material how elastic a material is or how plastic a material is. You may also need to learn few things about bioyield point, the rupture point, and the point of inflection. So let me try to show you the graph first, and then we will come back to this slide to read the definition. So you have a stress or the strain or the force or the deformation curve. This is an ideal solid, like a metal. So it goes all the way up and come back, right? So that's the elastic limit, perfect. So these are biological material, right? So in a biological material, first of all, it's not linear. And then it reached a point, and then there is a slight drop. That is the bioyield point at which there is a microscopic damage to the cell walls. And then it keeps increasing. And then there is a point at which it completely ruptures and breaks apart. Okay? But this bioyield point is not going to be seen on each and every FD or stress strain curve. For example, here is a softwood. You couldn't able to see the bioyield point at all. It directly went to the rupture point. So the bioyield is the microscopic damage. Example, the cell wall rupture. The rupture is a macroscopic damage, which is the crack and fissures and fractures. The point of inflection is the point at which the slope of the loading curve is maximum, meaning that the second derivative of the curve is 0. The slope is maximum, that means the second derivative is 0. So you look for that maximum slope and you call that as point of inflection. Okay. There are few more properties you need to understand. Is the yield stress. The yield stress is the stress at which the strain becomes plastic. So for example, if we go back to this curve, this is yield stress. Sigma y is the yield stress, which is a property of a material. A simple stress is not a property of a material, whereas yield stress is a property of a material at which the material starts to yield, becoming plastic. So if you are designing a material that is going to undergo the load in a mechanical system, let's say to harvest, you want the stress to be below the yield stress because you don't want a permanent deformation. So if it is a bridge, when the truck goes by, there is going to be a little compression on the pillar, but you do want it to rebound it back within the elastic limit so that when the next truck comes in, it press it back and rebound it back, and there is no permanent damage, and then it can last for a long time. Okay? And the another one is the ultimate stress. The ultimate stress is the maximum stress before it ruptures. Definitely you don't want to reach it. That is this stress, right? This is the rupture or the ultimate stress. That is also a property of a material. The another one is a modulus of resilience. It is the elastic energy that a material absorbs during loading and subsequently releases when the load is removed. So this one you want to plot it on the FD curve. F is in Newton. The deformation or delta L, let's say plotted in meter. Let's say you have a curve like this. Okay. And if you determine the area under the curve, that is Newton times meter is joules. So it's basically the energy required to move it up, which is the energy that is absorbed by the material during the loading. And when you release it, it goes back to 0. That means it releases the energy back. That is known as the modulus of resilience. The force deformation behavior or the FD behavior or the stress strain behavior, it is related to moisture content, right? So typically the moisture content has an inverse relationship with the modulus of elasticity. Higher the moisture content, the lower the modulus of elasticity. The strain rate is basically if I plot stress versus strain, okay, and let's say this is at a strain rate of 1, meaning that the rate at which I'm creating the strain. So if I have a material and then if I move ahead, how fast I am moving the head is the strain rate. Okay, so if the strain rate is higher, typically the curve line moves up. So this is the higher strain rate. This is the lower strain rate. So typically for a given strain, at a higher strain rate, you need a more stress.